A lot to do today. We're going to be looking at setting up some differential equations, get some practice with that. We're going to learn some terms. We're going to see like, ooh, things can get really weird. So let's be careful. And also doing some practice of differential equations of the form y prime equals something just involving x. And you're like, whoa, that seems really familiar. Kind of like the stuff we did in Calc 1 and Calc 2. Because it's the kind of stuff we did in Calc 1 and Calc 2. So it should feel really familiar. And hopefully, that means we'll do really well on it. Right? Right? Of course, no problems. No problems. All right, well, let's begin. All right, so our first example. Let's set up a differential equation for the curve y equals f of x, which satisfies that the tangent line to the curve at a point xy hits the axis at the point 3x comma 0. And there's a second part which we'll get to in a minute. First, let's get the first part here. So what we're after some curve which has a property. All right, well, let's talk about this. So we should get some intuition going. So we say, okay, well, what property do we want? So we say, okay, let's say here's our plane. And what we have is some curve doing something. We don't know what our curve looks like yet. But that's okay. That shouldn't stop us. We should say, well, let's just draw something. It may or may not be reasonable. That's all right. And so, okay, maybe that's what it looks like. And what's the point here? The point says, look, suppose you come to this point on the curve. So here is our point where it's at x and y. And this is the curve y equals f of x. And it says that if you take the tangent line to this curve, it's going to hit the axis at a particular point. All right, so we draw on our tangent line. And it says, look, it's going to hit it at the point 3x 0. So in other words, however far out you were here, you're going to go 3 times as far out, and that's where the tangent line hits. All right, well, okay. Now, we start thinking, what do we do? What do we do? Well, we know we're after a differential equation, and so what we start thinking about is, all right, what do we need? Well, a differential equation says you have something involving a derivative. I mean, that's the idea. So say, okay, well, let's think about y prime. We say, oh, all right. What does y prime have to do with this problem? I mean, that's important. When we're thinking about differential equations, we have to say, okay, we have this derivative involved. It represents something. Can we see what it represents and connect it to what's going on? Now, in our case, we say, okay, well, what is y prime? We might say, well, it's dy dx, all right. It's rate of change, okay. And we keep going down our list and say, oh, there's a nice graphical way to think of the derivative. So y prime, we can think of it as being the slope of the tangent line. Like, well, what? Slope of tangent lines? Well, our problem involves a tangent line. Good. So that's probably a good interpretation. So we say, okay, great. Y prime, that's our slope of our tangent line. All right. Now that doesn't mean that we have our differential equation, but we have something that makes sense. It's connecting to what it is that we're doing, right? Because, that's what we want to do. We want to connect to our problem. All right, well, how do we finish up? Well, we say, okay, well, what we need to do is to somehow say, all right, what is that slope? And normally, we have to find the derivative and so forth. We can't do that. We say, but we don't need it because to find the slope of a line, we need 2 points. And we have 2 points. We have this point x comma y, and we have that point 3x comma 0. All right, great. So we look at this and we say, okay, what's our slope? Well, we need to look at our rise. How much do we go up and down? And we need to look at our run. So how much did we rise? Now you might say, why? Well, because we need to know, right? We're looking for an answer. That's why we're asking the question. But really we meant, okay, the variable y. All right. Now, the question is this y or is this minus y? And the answer is, well, it depends on how you look at it. Because when we're talking about rise and run, we really are talking about in comparison of 2 points. So the question is, which point is the first point, which point is the second point? And then we can have our answer. So normally we like to move from, left to right. Okay. So here we say, all right, if we're moving left to right, we say, all right, what we would do is that we could think this is our first point. Here's our second point. Our rise, well, we went from y down to 0. So we would say negative y. Our run, we went from x to 3x. So that would be 2x. And say, okay, so we get y prime is equal to rise over run, negative y over 2x. Or y prime equals minus y over 2x. Good. And I'm going to make a note here. This is for our tangent. Great. Good. So we have it, because this is a differential equation. It's a differential equation that connects our curve. The curve with this property has to satisfy this fact. Y prime equals negative y over 2x. Beautiful. All right. Now there's a second part to this problem. And the second part says, well, what if instead of the tangent line, we use the normal line? All right. So the key thing to understand to get started here, of course, is what is normal here? When we talk about normal, what are we referring to? So normal, the key word here really is perpendicular. So that's what the normalized line is. It's perpendicular to our curve. So instead of our curve looking like this, we would really want our curve to be perpendicular somehow. So that's what we'd want. So we say, okay, so we don't need to do a lot of work. We have most of it there. You say, okay, look, that says we want to have it be a negative reciprocal, right? Because two slopes are perpendicular if they're negative reciprocals to each other. You say, all right, so if we start with this slope, that's our slope, take the negative reciprocal, flip it over, that'll be our slope for the normal line. So that says, all right, we need to have our derivative be 2x over y. And there we go. There's the normal. Okay, so we'll make some note here. This is negative reciprocals. All right, good. And we're done with the problem, right? Now, we have some space here. Let's make some comments, because I think there's something really interesting that's going on here, and it's fun to point this out. Okay, so what's the interesting thing? Well, suppose we were good at solving differential equations, and we're going to get good. We're going to get better. In fact, these particular differential equations are just like the ones that we're going to be able to solve in the very near future. So if we took this one, y prime equals negative y over 2x, well, it turns out that the general solution has the form y equals some constant divided by square root of x. All right, so that's what it looks like. Okay, now what about this other one for the normal? Well, again, we'll be able to solve this soon, very soon. Well, what does a general solution look like? Well, it looks like y is either plus or minus, just depending upon what happens. We get to pick based on the problem. 2x squared plus a constant c. All right. And now you're like, okay, that's adorable. But is there anything else we can say? And yes, this is the part that goes like, wow, cool. Now, what we can do is we could say, if we were good at drawing, and unfortunately this is the part where I'm probably not going to be the greatest at drawing, but at least I can explain the idea. So constant over square root of x. Okay, great. Well, gets a little bit messy. So it looks something vaguely like this. Of course, plus or minus. As it's written here, we can't have negative solutions, but you can imagine we could have made this the absolute value of x. It would have been fine. But for now, let's just say here's some curves. And now you have square root 2x squared plus c. Well, what does that look like? Well, one solution is a very simple as straight lines. It's a little bit steep slope, so if c equals 0. And of course you have some other solutions. And so they're hyperbolas. And so you get these things going on. Now, what's the great ooh? Well, the great ooh is the following. If we look at where these curves intersect, what's going to be true at these points of intersection? What can we say? Can you see it? They will always be perpendicular to each other, because that's how it's set up. Because what's happening here is that when we look at these intersections, one of them has the tangent line be the normal line to the other. And so their tangent lines in particular have to be perpendicular. So now it's like, wow, we have these two families of curves, and when we plot them, they're mutually perpendicular at every single point of intersection. And so that's kind of a cool idea. It's like, hey, is it possible if I construct this family of curves, I can come up with a new family of curves that always intersects perpendicularly? And now we're like, yes, you say, okay, what's the differential equation the first family solves? Flip it over, take the negative reciprocal, and solve that differential equation. And now the resulting curve will always intersect perpendicularly. I think that's beautiful. I think that's beautiful. Amazing, amazing thing. All right, good. So that's a nice, fun example. Okay, well, we always want more, right? We're not satisfied with just one example. Give us more. All right, we can do that. So, our next example. Set up a differential equation to model the following situation. Now, the nice thing is we're just setting it up. And so we don't actually have to solve. We just have to say, okay, here's what the differential equation is. And here we go. A rumor is spreading through a community with a fixed population, P, where the number of people who have heard the rumor so far is W. All right, great. Now, at any given time, the number of people that learn about the rumor is proportional to the square root of how many people have not yet heard about the rumor. All right, good. Okay, so we have this statement. Now, a lot of people look at this and say, oh no, words! I didn't start math to learn words! No! On to the next one. It's like, no. We're going to do this. In fact, this is a really important skill. Because what we want to do is translate this sort of descriptive language into a nice mathematical expression. Because we have this machinery in place that says, okay, here's how we can work with these mathematical expressions. Now, if you go back hundreds of years ago and look at really, really old math books, they use lots and lots of words. So it was really cumbersome to read through it because they really hadn't yet sort of adapted this idea. It's like, hey, there's this nice condensed format with these equations. But now we know better. Okay, so what are we going to do? Well, we're going to go through and just learn to parse. And even though it looks a little intimidating, it says, look, it's not so bad. Let's just go through it piece by piece and put it all together. Let's see what we get. Okay, so let's start with the first part, the first sentence, which is telling us sort of the setup. It says, a rumor is spreading through a community with a fixed population P. So notice we have P. And what can we say about P? Is it changing or is it constant? And the answer, it's a constant. Now, how do we know? Well, the word fixed, that's telling us it's a constant. Okay, great. Progress. Now, there's something else. the number of people who have not heard the rumor. Oh, sorry, the number of people who have heard the rumor. Excuse me, I've gotten ahead of myself. The number of people who have heard the rumor so far is W. Okay, now is W fixed or is it changing? And this is the part that changes. Okay, so good, because you may not have heard about the rumor, and then you heard about it. Okay, so now you've changed the value for W. Okay, so now the next sentence is really an equation, and we just got to figure out what all the parts translate into. So let's begin. All right, so at any given time, so we're just saying, okay, what's happening in one moment? We have the number of people that learn about the rumor. All right, good. So that's something. The number of people who learn about the rumor. What is it? Well, it's something to do with W, right? Now, is it W? And why not? It's not W. Okay. Because what W is, it's the total number of people. That's everybody who know about the rumor. What are we looking at? We're looking at the number of people who have learned about the rumor. So in other words, it's the people who have just been sort of informed. They've just started learning about it. So what is being captured there? Well, it's W prime. It's how W changes. So when you see something that says, oh, this is a change in something, what you're really looking at is, okay, we capture that by the derivative. So W prime. That's that first statement. All right, great. Progress. Progress. Good progress. All right, the next one is very short, but also very important. Is. All right, what does is correspond to? Equals. So when we have something is something, that really means these two things are equal to each other. So W prime is something. W prime equals something. All right, great. Now to our next part. Okay, proportional to. Now that's an important phrase. What do we mean when we say something's proportional to? Well, what that indicates is that there's some constant that you're multiplying by. Now, that's not part of our setup, so we just introduce a constant. So let's use K. K is a very popular constant. So it's proportional to is some scalar multiple up. All right. Now, the next part is the sort of, the square root of. All right. Great. Well, that means that there's a square root involved. Okay, we can do that. That's not so bad. Square root of. And now we're near the end of our sentence, right? We're running out of space. There's not a lot of real estate left. So what is it? The square root of what? How many people who have not yet heard the rumor? All right, now we got to think about that. Because that's not W. W is how many people who have heard. How many people have not? Well, we can say, look, let's think about, we have our whole population, and we know how many people have heard about the rumor is W, so it's everybody else. And so that would be our population subtract W. And that's it. We're done. We've translated the sentence into a formula, and that's set up our differential equation. Now, this is a differential equation, by the way, where we weren't told any initial values. That's okay. Sometimes we don't have initial values. But we have the right differential equation. And there you go. See, it's not so bad. So don't be intimidated by word problems. Word problems are not meant to punish you. It's just a matter of saying, okay, let's take the statement and let's break it down. And just say, okay, what does each individual piece represent? And we put it together. So once you practice, it's pretty straightforward. But practicing is important. The more you practice, the better you get. It's true in differential equations. It's true in life. All right, well, let's move on. Now, not practice, time to pick up some vocabulary. And words are important. Oftentimes, the reason that we have these terms is to really give a nice descriptive way to talk about what's going on. And so we're going to talk about certain words that are going to show up fairly frequently as we go through and talk about differential equations. So this is not our full list of vocabulary words. We're going to keep expanding our list as the semester goes on. Generally speaking, when we add certain terms, it's mostly to say, here's a description of what we're talking about, and also to say, hey, here's this interesting group of differential equations which have common properties. And usually what that means is they also have common ways to solve them. So when we start seeing terms, it's like, ooh, I think there's going to be like a nice idea about how to solve this kind of differential equation coming up in the near future. So that's what you should see when you see terms popping up. It's like, okay, a new idea is coming. Well, but let's just start with some basic terms. So the first one, the order. So when we talk about the order of a differential equation, what that's referring to is the order of the highest derivative. You might think about another place where we've talked about order in math. We talk about the order of a polynomial. And you say, oh, well, that's the highest power. And so it's similar to that, but now we just do derivatives. So it's not so bad. You look at your expression and you scan it and you say, okay, what's the biggest derivative I see? That's the order. So for instance, we might see something like y prime cubed plus 3y double prime x to the 7 and equals cosine x y to the third power. All right, there we go. I'll just make one up. Okay, what's the order? Well, we start scanning and saying, okay, where's our derivatives? And we see two places where derivatives show up. So one place we see a y prime, another place a y double prime. Okay, which one's bigger? The y double prime is the bigger derivative in the sense that it's two derivatives. So we say, okay, then this is a second order. So second order means the highest derivative is a second derivative. First order would be the highest derivative is a first derivative, and so forth and so on. So this is a second order. Now, don't always necessarily have to be the case where the highest derivative is at the front. It doesn't have to be. You might say, well, wait a second, here's like a seventh power, right? Shouldn't that count? No, because we're looking at derivatives, not powers. And here you might say, well, look, this one's being cubed. Again, no, we're looking at derivatives, not powers. So look for the highest derivative. Now, on a side note, while we're here, you might notice that there can be some confusion. This y double prime kind of vaguely looks like y to the 11th, right? If you weren't careful, you'd say, oh, wait a second, is that y to the 11th? No, let's be careful. And so the notation that you'll see, if you start getting a really high derivative, they have a different way to write it. So, for instance, if I wrote down y and then upstairs a 9, but I put that 9 inside a set of parentheses. Well, that's referring to a derivative. So this is the same thing as saying y, where we put 9 little strokes here. Of course, I probably should have counted. I think, there we go, I think that's 9. And you'll notice this is a lot more clear that it's like, hey, there are 9 derivatives here. Then, you have to sit here going, 1, 2, I think 9, maybe 8. Let me count again. So that's a notation that you might see. So if you see parenthesis up there in the exponent, that's referring to a higher order derivative. So just keep that in mind when you're looking at your notation. All right, good. So now we know what we mean when we say in order. And the majority of the time this semester will be either first order or second order. From time to time, we might dip our toes into third or fourth, but not really too much. We're already going to have enough of a challenge with just first and second, so we don't need to work too hard to challenge ourselves. Okay, so the next bit of terminology. Ordinary differential equation versus a partial differential equation. Now, what's an ordinary differential equation? Well, an ordinary differential equation is the kind of differential equation that you see walking around on the street, right? Because it's ordinary. No, that's not quite what we refer to. So ordinary differential equation really is more of the first kind of differential equation you might encounter. And so think about the first kind of things that you see in calculus are functions of one variable. So that's what we're really referring to. So ordinary differential equations are when we're after something of the form y equals a function of x. And so how do you denote these? Well, usually you'll see things like a y prime, or you'll see things like a dy dx, or, occasionally you might see something where there's something called just capital D that gets used to say, oh, it's the derivative operator. This is not quite so common, but, well, things exist. If you go back to Newton, he was would do something like this, y dot. Well, okay, dot is kind of a very rare notation, but it exists. So, but most of the time, this is the kind of thing that you'd see. All right, so that's an ordinary differential equation. Differential equation where we have functions y equals f of x. But you might say, hey, the world is complicated. Very rarely is the case that when we're taking real world measurements, we say, oh, this thing only depends on one input. It should really just say, oh, this thing depends on multiple inputs. So maybe it says, look, it's not just location, it's location and time. Or maybe it's location in 2 dimensions. So we have an x and a y. Or 3 dimensions, an x, a y, and z. Or all sorts of things. So then we get into what's called a partial differential equation. So that's when our functions are something where we depend on multiple inputs. So we might have, let's just say, z is a function of x and y, or a function of x and y and t, are just, the point is multiple inputs. So why do we call it a partial differential equation? Well, really, this comes down to partial derivatives. So this is something that you'd see if you take a class in multivariable calculus, where the idea is we're going to look at derivatives, but we say, look, because there's multiple variables involved, you don't take derivatives of everything simultaneously. What you do is you take the derivative of one of the variables at a time, and you treat all the other variables like they were numbers. That's how partial derivatives work. In other words, it's like the easiest thing to do. It's like, oh, hey, just think of one thing changing at any given time. Now, how do we do that notationally? Well, you don't use the prime. The problem with the prime is it says, well, take the derivative, and when there's only one variable, it's like, okay, great, I know what I'm doing. When there's multiple variables, and you say, take the derivative, and you ask, which one? X? Y? Which one? Okay, so that's why you won't see prime. Now, there is a similar notation here, so you might see something like partial z, partial x. So this symbol is really a derivative symbol, where it says take a derivative. It's the same philosophy as what the d here is, just saying a small change in it, but it's sending a signal that says we recognize that this is a function which depends on more than one input. So that's the difference in notation. Other common things you'll see is instead of the y prime, you might see something like a z sub x. All right. So this subscript here is just indicating you're taking derivative with respect to x. You might see d sub x of z. And again, this is saying the derivative operator of the variable x, and you apply it to z. All right. So what does one of these look like? So one example you might encounter, zxx plus zyy equals 0. So this would be an example of a partial differential equation because it involves partial derivatives. And we can even say it's a second order partial differential equation because this notation says you're taking 2 derivatives with respect to x, and here we're taking 2 derivatives with respect to y, and we put it together. All right, great. So, on a side note, we will almost never talk about partial derivatives in our class. We'll mention them a couple of times, but we're not going to be solving partial differential equations. If you want, there are courses about it, and there's a lot of interesting things to be said. There's a lot left to solve in differential equations. There's many things we don't know how to solve, which is great. That means there's still problems for us to do. So we're going to focus our energy on ordinary differential equations. So summing up the first 2 points, we're going to spend most of our time doing first order ordinary differential equations or second order ordinary differential equations, oftentimes abbreviated as ODE. So if you ever hear someone say an ODE, that's what we're talking about, ordinary differential equation. The last thing is just a little side note that says, what is the normal form of a differential equation? And it's actually kind of intuitive. And if you look at it, it might confuse you more than anything else when you say, okay, what does it mean? Well, it says, look, get the highest order derivative by itself. So if I'm a first order ordinary differential equation, I would say, look, get the highest derivative y prime as a function of x and y. And now you start thinking, oh, what does that really mean? So what this really means here is the following. It says, take y prime and write it as stuff involving x and y. That's what we really mean. Now, it might be the case that it only involves x. It might be the case that it only involves y. But when we write things in normal form, it just says, hey, take that highest derivative, get it by itself, and now we say, okay, y prime equals stuff with x and y, or y double prime equals stuff with x and y and y prime. That's what you mean. That's what normal form means. All right, good. So now we have some new terminology, and so now when you call up your parents and you say, hey, here's what I'm studying, second order ODE, and they'll be like, what's that? And now you can explain. And it's like second order means, hey, we're taking two derivatives, and ODE says, oh, our functions only involve one variable. And of course they'll probably say, oh, that's nice, but when are you coming home? We miss you. So, gotta love parents. They're such great people, wonderful people. All right. Now, as we keep going in our differential equations, we should recognize we might run into problems. And so we're going to talk about some problems we run into. What's the ideal thing? Well, the ideal thing is we have a differential equation, which means that we have, in particular, we have y prime is some function of x and y, and we have some initial condition y of a equals b. And what we'd like, well, is we'd like to have some unique solution. That would be the ideal. That would be like, oh, if we could get that, life would be so good, we would be happy, and we would be like, yeah, we found it, we found the one solution that works. But that may not happen. So we just want to say that, some things can go wrong. Okay, so what could go wrong? Well, we want a solution. One thing that could go wrong is that there are no solutions. So here's a very simple example of how that could be disastrously wrong, right? So suppose our differential equation says y prime squared plus y squared equals -1. I'm not even saying any initial values. I'm just saying, hey, this is what we want. Is there any solution to this? No, because if we square something and add them together, we have to end up with something that's non-negative. So we can't end up with a -1. All right, so there can't be any solution. Now this is one thing where we have non-existence. Sometimes it depends on initial conditions. So it says, well, it might work with some initial conditions, it might fail with other initial conditions. So keep in mind, it's possible no solution exists. Now, the other thing that can go wrong, which is sort of the opposite extreme, which says, hey, we might have many solutions, right? So we really wanted one. We wanted a unique solution. And then it's like, oh, well, there's like a million or two, or, there's more than one. And, okay, well, let's convince ourselves that it's possible. And so here's an example. Suppose we consider the differential equation y prime is 4x times square root of y. All right, that's a differential equation. We can talk about it. And y of 0 equals 0. All right, so what are some solutions? Well, here's a claimed solution, y equals 0, which means you're the axis. Well, how do you check if something's a solution? Well, you have to check, does it satisfy the initial conditions? Well, here's the initial condition, does it satisfy the differential equation? Okay, well, the differential equation is pretty easy to check, right? The derivative of 0 is 0, square root of 0 is 0, 0 equals 0. Initial condition, well, when you plug 0 into the function which is always 0, you get 0 out. So yeah, that's a solution. Good, works out. Okay, how about x to the fourth? Well, that's a different function. X to the fourth and 0 are not the same function. X to the fourth vaguely looks like x squared, so it kind of looks like a big smile. All right, so here's x to the fourth. All right, well, okay, initial conditions. Plug in 0. 0 to the fourth is still 0, hasn't changed. All right, derivative of x to the fourth, 4x cubed. Then we have 4x. The square root of x to the fourth is x squared. So 4x times x squared is 4x cubed. So yeah, that also checks, which means that we have now two different solutions happening at the same initial value problem. So remember, initial value problem is you have a differential equation and a initial value that needs to be satisfied. All right, so now we're like, things can go bad. All right, but there's good news. Now the good news is if we start with something which is reasonable, and we're going to talk about reasonable in our next meeting here, but if we're reasonable, then we're going to get a solution and it will be unique. And so that's the good news. One thing to keep in mind, and we're going to talk about this in an example in just a moment here, is that, hey, it might be a unique solution, but you have to keep in mind that you may have to make some assumption about the interval. So sometimes you'll come up with a solution to a differential equation and say, oh, like this works like everywhere and life is good. And the answer is, well, no, it's not quite that case. It's a good solution up to some point, and then something can happen. Now, we'll talk about things which can happen. Let's not ruin the surprise, right? We should encounter it. So we're going to talk about, okay, we'll get a unique solution in some appropriate interval. And so, all right, let's look at some examples of things that can go wrong in the sense that, well, we can't really have a solution for all values, and so that we're aware of things to come. We want to be, we want to know the dangers that lurk ahead, so we know when to spot them and know how to handle them. That's what we'd like. All right, we're going to look at two in particular here. So let's look at our first one. So our first example here. So verify that y, this function, which has the form 1 over a constant minus x, is a solution to the differential equation y prime equals y squared. Okay, now let's just do that, right? That's like a whole problem in that one sentence. So here we go. So we're looking at y prime. So that says we're taking the derivative. So I'm going to just say, well, what is y? It's 1 over c minus x. So 1 over c minus x prime, taking the derivative of 1 over c minus x, which, if you want, you can write this as c minus x to the minus 1. We're taking the derivative of that. Okay, all right. Well, that's c minus x, which is a function, inside the function to the minus 1 power. What rule do we need? We need the chain rule. Function in a function. Great. We can do that. Okay, so we bring down our exponent, minus 1, c minus x to now minus 2, because we subtract 1 from the exponent, and multiply by the root of the inside. All right, well, the root of the inside is minus 1. And so we're in math, so 2 wrongs make a right. Well, no, but 2 negatives make a positive. So when we multiply a negative times a negative, we get a positive. And so what do we have? Well, we really have c minus x squared downstairs, because that means move it downstairs, that negative sign. So this could also be written as 1 over c minus x quantity squared. Say, well, wait, 1 over c minus x, that's another name for y. So this is y squared. And now we verified y prime equals y squared. Done. Done. All right, so verification complete. Now, the next part. Find the particular solution which also satisfies that y of 3 equals 2. All right, so we're told y of 3 equals 2. Well, okay, how do we find y of 3? Well, that would be 1 over c minus 3, because we're plugging in x equals 3 into our expression. So now we need to solve for the constant c. Because what we really have here, when we have this y equals 1 over c minus x, is we have a collection of solutions. There's many solutions. And so for each choice of c, there's a different curve. And so we're saying, okay, we want to reach in and pluck just the right choice for c so that our curve will pass through that point and be in this form. Okay, well, right now c is in the denominator, so let's just flip things over, and we'll do it on both sides. So we can say, okay, great. Another way to write this is that c minus 3 is a half, or we could say c equals 3 plus a half, which of course, in elementary school we would say 3.5, but then we said, oh, well, we write that as 7 halves. So 7 halves. Great. Good. So that says, that's our choice for c. Now remember, when we talk about a solution, we're not after the c, we're after the function. So we're going to take that c and put it in. So that says our solution is y equals 1 over 7 halves minus x. Now, if you don't like fractions within fractions, you can get rid of this fraction within a fraction by saying, okay, what do I need to multiply by to clear out that 2 downstairs? I've got to multiply by 2 because there's a 2. So if you multiply top and bottom by 2, then you'll get another way to write this function. It's the same function. It's just writing it in a different way. 2 over 7 minus 2x. All right, great. So that's the next sentence, right? Find the particular solution. All right, good. We found it. And then there's this last question. What can we conclude about y of 5? Now, what do we want to do? Okay, let's be honest here. If we didn't know we were talking about problems and we were just sort of like humming and hawing through, we'd be like, okay, I got the function. Let's plug in 5. And we'd say, okay, well, at 5, it seems to be 2 over 7 minus 2 times 5. That's 7 minus 10. Okay, that's negative 3, negative 2/3. Seems good to me. We got an answer. But is it valid? Are we allowed to do that? So here's where we have to be a little bit careful here, because when you look at this function, you should be like, oh, there's some problems with this function. What do you notice about this function here? Can you see anything? Something that makes you say, well, in particular, one thing is there's an asymptote. So this is a function with an asymptote here. And you have to keep that in mind. So let's look at this function a little bit more closely. So what's going on? So we have the following. So here's our plane, our grid, and say, okay, where's the asymptote at? Well, it's at 7/2, right? Because if you plug in x equals 7/2, you'd have a divide by 0. Okay, so we say, all right, there's an asymptote here at 7/2. And now, well, you can plug in some values, and what you'll see is that our graph looks something along the lines of the following. So it comes up and then does that. Okay, so far, nothing that makes us say, hey, wait a second. And let's also mark where's our initial condition. And our initial condition is at 3. Now 3 is below 7/2. So here is 3. And so our initial condition says when you plug in 3, out comes 2. All right, so there we go. Now, where is 5 in this picture? Well, it's on the other side of the asymptote. There's 5. All right, so now our discussion here. We have this function, and we can write this function. We say, look, this has a function, and as a function, it's valid for every x other than 7/2. But that doesn't mean it's a solution to our differential equation for all x other than 7/2. And here's the idea. When we talk about a differential equation, you should think of it as saying two things happened. The first thing that happened is we started someplace. That's our initial value. So it's like, look, you're starting here. That's where you begin. The second thing that happens, okay, so after you start, the second thing is you move. And that's what the y prime is telling you. It's telling you, here's your behavior about how you change. So I should start and I move along the curve. So what happens? Well, our solution will be valid to wherever we can legally move. And in particular, we have to be able to move without lifting. Because if you lift, well, that's a place where you can't connect. You have to be able to connect. And you'll notice that as we move up here, you'll be like, oh, gotta pick up and put back down and start again. There's no connection. And therefore, our solution stops at 7/2. We can't get over this asymptote. But we can move along the curve to the left of 7/2. And there's no other issues. We'll talk about some other issues that might occur, but for this function, it's a very nice function. So we cannot make any conclusions about y of 5 in terms of the differential equation because y is the solution to the differential equation. And so what we really should mark down here is to say, look, this is our solution for x below 7/2. So if we'd asked what happens at 0, what happens at -2, what happens at -100, we can answer those questions. But as to what happens at 5, we are like, no, we can't answer that question in terms of a solution to the differential equation because there's this gap that we can't get over. We cannot get past that asymptote. All right, so watch out for asymptotes. They're going to give us restrictions on where our solutions are valid. All right, so that's one thing that can happen. But other things can happen too. So on to more examples. All right, good. Our next example. So we're given that xy prime equals 4y. All right, that sounds pretty harmless as far as the differential equation goes. And we're asked to find a general solution for y. Okay, now I will tell you we don't quite yet have the right tool. So we're going to pull out our favorite thing right now, which is our black box. And we'll ask the black box, what's a solution look like? So xy prime equals 4y. Okay, so we're going to feed that into our black box here. Let's put our box. There we go. There's our box. Okay, and now what comes out? Well, the claim is y equals some constant x to the fourth. All right, well, let's check that. So, what's the derivative of a constant times x to the fourth? Well, the 4 comes down, constant x cubed. So, 4 times constant x cubed times x gets us to 4 times constant x to the fourth. On the other hand, 4 times constant x to the fourth is 4 times constant times x to the fourth. So these two agree. Good, good, yes. So there's a general solution. Many solutions, right? You choose a choice for C, boom, we can tell you what's going to happen. And all right, great, wonderful. We got the first part done. Now, the next part says, if we are also given that y of 2 equals 3, find a particular solution. All right, great. Well, let's take a look. So y of 2 equals 3. So what happens? Well, okay, so we're gonna take our nice general solution and do what? Well, at x equals 2, well, we're going to get 3 equals some constant c times 2 to the fourth, or we can solve c equals 3 over 16, because 2 to the fourth is equal to 16. Okay, so now we say, great. So we get, here's a nice solution. Y equals 3/16 times x to the fourth. Wonderful, wonderful. All right, so we found a nice general solution. We found a particular solution which passes through the point that we want. In other words, it satisfies our initial conditions that we're interested in. And now, what can we conclude about y of -1? Now, what we want to do is we say, oh, we plug in -1. -1 to the fourth is 1 times 3/16. 3/16, and we're done! But there's this phrase, careful! Exclamation mark, exclamation mark, as though we should be careful. So maybe we should be careful here. What's weird about this? Because it doesn't feel weird. Why do we need to be careful? Okay, so before we try to make any conclusions, let's come back and take a look and see what our solutions might look like. So in other words, instead of focusing on one solution, let's pick some different values for C and see what's going on. Okay, well, all right, I could pick C equals 0. That's a great choice. And 0 is oftentimes that should be one of your first go-tos. Hey, what happens if C is 0? Well, we get y equals 0. All right, well, that's not so hard. That looks like that. All right, how about 1? C equals 1. Can we graph that? Yeah, x to the fourth. It looks kind of like a parabola. It's slightly stretched a bit, but yeah. Okay, there's C equals 1. Okay, how about C equals 2? Okay, well, 2 times x to the fourth, it's now even more stretched. All right, great. How about a half? All right, okay, yeah, we can do that. Sure, no problem. That would be like squishing our curve. Okay, so half, we come down, and it looks something like that. And now someone might say, hey, how about a negative value? Okay, sure, -1, right? Well, that would just be a flip. And you might say, okay, what about like -2? Okay, sure, why not? We can do that. We have the tools, we have the technology, and you might be, okay, how about -1/2? All right, okay, we can do that too. All right. And at this point, you're like, all right, what do we see about all these curves? What's happening with all of these curves, every single one. They all have something in common. And this is important. This is the key thing. The thing that makes it frustrating. Can you see what they all have in common? They all go through the origin. So they all pass through this same point. All right. Now you might be like, oh, what's so bad about that? And here's the issue. So our particular curve, now if you look at what is 3/16, it's smaller than a half. So our particular curve, it's actually this curve down here. Okay? And we have our initial condition. Let's say that's our initial condition. When is this solution valid? Well, it's valid for quite a while. If we kept going up, it'd be okay, no problem. And if we move towards the origin, we're fine. But the problem is that once we hit the origin, which way do we go out? We could follow the same curve in some sense that we started in, but I could have moved, I could have moved on any one of these curves that come out. So what happens is when you have multiple solutions intersecting at a point, what happens is you can come in one way, but you have multiple ways to get out. And so you lose information. So your solution is valid only up to that point. So our solution is valid here for all x greater than or equal to 0. Because once we go below 0, we don't know which curve we should have taken on the way out. So be careful when you have solutions crossing. And I will say this is not very common. And there is something very interesting about what happens at x equals 0 in terms of this differential equation. It's something that we can talk about in our next time we get together. But that's just another thing to be aware about. Okay, so we've talked about things like watch out for asymptotes, which we can also say things like watch out for vertical tangent lines, or something similar, because our differential equation basically becomes undefined at that point. And then watch out for solutions crossing, because once solutions cross, you lose information. And so those are some things that we should be aware of that limit how much we can say. You know, it restricts our answer for when our solution is valid. Now, I hope you don't walk away saying, oh man, things are going to be bad here. It's like, most of our differential equations are going to be tough. They'll be hard to solve, but these are cases where they've been kind of engineered to have things happen. In a lot of cases, things work out pretty nicely, and it's valid for many choices of x and y. And as we go on, we'll see more and more examples. And we'll get better at it, right? We're newbies, we're beginners. The more we do, the better we're going to get. We're going to be amazing by the end. All right, so last topic, but we'll take our time because we want to do some examples here, is talking about the very nice differential equations. So these are differential equations when we have y prime is a function of x. And we like these because we kind of know how to solve them. Because this is going back to our good old Calc 1 and Calc 2 days. In these kinds of differential equations, we say we're really looking for antiderivatives. So our general solutions look like integrate our function, or really take an antiderivative of our function, and remember that there's a plus c. All right, wonderful. Now we can also do particular solutions. In fact, we can write a particular solution in a very nice condensed way. So what if we have our initial condition says that when we plug in x equals a, we get b out. Then we can write our particular solution in this really nice condensed form. Namely, as our function is b plus this integral. Wow, that's it. That's the whole thing. Let's verify it. So let's check, first off, our initial conditions. Initial conditions are often easier to check. When you plug in a, that would be b plus the integral from a to a. of f of t dt. Now what do you get when you integrate from a to a of f of t dt? What does that equal to? 0. No, that says, look, I start and I stop at the same place. I haven't had a chance to accumulate anything. That's what our integrals are. They're cumulative totals. Well, I can't accumulate if I don't go anywhere. So this second part equals 0, and we get b. Wonderful. All right, so that shows we satisfy the initial condition, but we also need to show that we have the right derivative. So I say, okay, well, what is y prime? So that says you're taking the derivative of b plus the integral from a to x of f of t dt. Well, what's the derivative of the constant b? 0. Okay, that's fine. What's the derivative of the integral from a to x of f of t dt? Do you remember that? It seems like it's a really important fact. One might even call it a theorem. And it seems so important, we might even say it's very fundamental to calculus. Yeah, it's the fundamental theorem of calculus. So if you recall the fundamental theorem of calculus, it's actually set up to answer the question, what is the derivative of the integral from a to x of f of t dt? And the answer is, it is f of x. And therefore, we see, aha, we satisfy the initial value, we have the right derivative, it's the solution that we want. Now, in practice, we almost never say, here's our solution. We almost always say, let's write our answer in this way, where we first off find the general form and solve for c. Okay, so let's do an example. So find the particular solution for the differential equation y prime equals x arctan x. Arctan, yes. I have a special place in my heart for arctangent. So I like to put it in when I can. Probably I put it in too often, but well, okay, we all have our weaknesses, but such is life. So y prime equals x arctangent x, and our initial condition is that y of 0 equals 2. All right, so let's go through and work it and see what happens. Okay, so what we really want is to say, okay, well first off, we're going to find our integral, and then the second off, we'll solve for c. So that's usually how we approach these types of problems. Okay, great. So we want to integrate x times arctangent of x. And at this point, we think to ourselves, that looks like a hard integral, and not the kind of integral we may want to do, because in some sense, integration is very hard. There's about 10 integrals that we say, look, if it's one of these 10, we're happy. And that did not make the list of the 10. And if it's not one of those 10, what we look at is we look for tools to help us rewrite it. So substitution is a great way to rewrite things like trig identities, going into algebra, things like partial fractions, all sorts of tools. And one of our tools is integration by parts. And so this is a great time for integration by parts. Now, you may think, ooh, it's been a while since we've done integration by parts. Can you review it? Yes, let's review it. So what's the philosophy for integration by parts? Well, when you think about rules for integrals, all rules for integrals came from rules for derivatives. And so the rule for derivatives, that's the product rule, became integration by parts. And so in particular, integration by parts is wonderfully set up when you have two things multiplying together. So it says if I have two functions, a function u multiplying by a derivative of a function v, so integral of u dv, this is the same as taking u times the function v and subtracting the integral of v times the derivative of u. So that's integration by parts. If you imagine taking the derivative of everything, you might remember the derivative of u times v, well, it's like u times the derivative of v, and then v times the derivative of u. And that's actually what we have, just rearranged the terms. So when you're thinking integration by parts, what you really are looking for is you're saying, hey, do I have two things multiplying together inside my integral? And moreover, is it the case that one of them is pretty straightforward to integrate, and one of them is like, I don't want to integrate that, but I'm happy to take a derivative. And if you have that, life is good. Life is good. You're ready for integration by parts. Now, in our case, we say we have our two things, our x and arctangent of x, and arctangent pops out to us and say, we don't want to integrate that, but lovely derivative. Such a lovely derivative. So we're going to let that part become the u. In other words, the part that we're going to take a derivative of moving forward, well, that means that the x is going to be the derivative of something. Okay, well, if dv gave us x, what would v be? Or if you like, what's the antiderivative of x? It's a half x squared. And then, of course, the other thing, what's the derivative of arctangent? This is good. What is it? 1 over 1 plus x squared. Amazing, amazing. No matter how many times I see that, it's like, what? That's so cool. Yeah, beautiful, beautiful. All right, so, well, what do we have? According to our rule, this would be equal to u times v. So 1/2 x squared arctangent of x. Okay, good. uv minus, and run out of space, so minus integral of v du. So v times du. So I'll say, well, there's a half, and then there's x squared over 1 plus x squared. All right, great. So in some sense, we started with an integral that involved x and arctangent, and after doing this rule, integration by parts, one time, we got down to an integral that feels a little bit more apples to apples, right? Like previously, x and arctangent felt like kind of like a trig kind of thing and a polynomial kind of thing, but now it's like, hey, it's polynomial stuff all the way. Feels better, feels better. Not that we're easy yet, but it feels closer, and so we should have tools to find this, right? Because we do. Okay, so now, how do we integrate? Well, one thing is to say, x squared is not that different from 1 plus x squared. In fact, the only real difference is 1. And so we say, okay, what if we put a 1 plus up here? Then it'd be really simple, right? 1 plus x squared, 1 plus x squared would be 1. And you should be saying, wait, I object. I object. You can't just add 1. You're right, we can't just add 1. But we can add 0. So what we'll do is add 1 and subtract 1 right away. That way our net change upstairs in the numerator is 0, and we haven't broken anything. But of course, we didn't add any 0. We added a well-chosen 0 in the following sense. Namely, I can think of it as two pieces, 1 plus x squared and minus 1. So what do we have? We have 1/2 x squared arctangent of x. That's the first term. Got to keep that going all the way through. And now we have minus, and we have the integral 1/2, and 1 plus x squared over 1 plus x squared is 1. That's why we chose that. And then minus 1 over 1 plus x squared. Now, if you don't like that idea, I will say that there's something else you could have done, which is you could have done long division. So if you prefer long division, good on you. It would still work. Life is great. But now all our pieces are in great shape for us to actually carry out the integral. So we still have that first term. We're not going to forget it. 1/2 x squared arctangent of x. Then we have the integral of 1/2 times 1. Well, that's going to be 1/2 x. Don't forget the minus. So minus 1/2 x. And now, don't forget the 1/2 still comes through, and the minus still comes through. So minus minus makes a plus 1/2. And the integral of 1 over 1 plus x squared is arctangent, right? Because we took the derivative of arctangent, got 1 over 1 plus x squared. So the antiderivative, all right, going the other way, arctangent. Great. And, of course, what else? Plus c. Plus c. All right, so this is our general solution. Good. Now, are we done? We did a lot of work, right? We should be done. It feels like it, but we're not ready yet. What else do we have to do? The other part we have to do is we have to find our particular solution, right? Because we need to satisfy that initial condition. And our initial condition being that when we plug in 0, we get 2. All right. So we're almost there. So we're going to now plug in 0. So 2 should equal y of 0. All right. Plug in 0. 0 squared, 0. All right. That's going to knock out the first term. 0, 0. Okay. Arctangent of 0 is 0. All right. Wow, that was pretty easy. So when you plug in 0, everything drops out except the constant. And so that tells us our constant should be 2. So we can now put that in, and we say, aha, our answer is 1/2 x squared arctangent of x minus 1/2 x plus 1/2 arctangent of x plus 2. And that is our particular solution. And we're done, which is good because we ran out of space. Wonderful, wonderful. All right, well, good. Now this one may be slightly more challenging, mostly because it's like, hey, let's practice that integration by parts that, well, we may not have done it in a while, but it's good to get that practice in because we're going to see it again and possibly many times. So the more we do it, the better we get. All right. Well, that's more practice, right? Another example. So find the general solution of the derivative of y with respect to x is 3x square root of x squared plus 9. So this is good. We only need to get to the point where it's plus c. We don't need to solve any initial conditions. So there's really just one step, right? So you say, hey, y prime equals function of x. Life is good. So we can say, look, our solution is you integrate 3x square root x squared plus 9. And that's what we need to do. Now, we start thinking, okay, how do we actually do it? And the first thing is we say, let's write this in a more calculus-friendly format. Well, what's not calculus-friendly? The square root symbol. We're more comfortable where we use, instead of the square root, something to the half power. Because when we talk about like rules for derivatives, rules for integrals, we're used to having exponents upstairs. So this is 3x times x squared plus 9 to the 1/2 power. All right. And now we start thinking, if we're really, really being like, we want to make things as hard as possible, you can do things to make things harder. You could be like, maybe trig substitution, right? Let's not do that. Let's not go there. What are some other things we could do? So we don't have to just jump to the hard things. You should always start with the easy things. Generally speaking, you ask yourself, hey, is this one of those 10 really easy integrals that we know how to do? And if it is, we do it, life is good. And then you say, well, maybe there's some algebra or trig I can do to make it look like one of those 10. And, okay, there's not really a lot of algebra that you can do. Now, do not do the following. And I know I'm telling this, I'm preaching to the choir because you're the good people, you're watching the videos. A lot of people make this mistake, and let's just go ahead and just let's just talk about the fact that people will do this. And there's temptation to say, oh, square root of x squared plus 9, well, that's like the square root of x squared and the square root of 9 put together, right? So shouldn't that equal like square root of x squared plus square root of 9, which is x plus 3? And the answer is no. No, don't do it. It's not true. This comes down to the idea that really things like exponents do not mix with addition. So you cannot break square roots up over addition. So don't do that. Don't make that mistake. All right, so there's no real algebra we can do here to make things simple. Okay, so going through the list. We checked our 10. Don't see any good algebra. Don't see any trig involved. The next thing you should look for is substitution. Substitution is such an amazing tool. It's our go-to tool, and probably one of the most, if not the most important tool in solving integrals. All right, so where do we look for substitutions? Generally speaking, we think about where did the substitution rule come from, and it came from the chain rule. So if we're looking for a good substitution to make, we think, well, for a chain rule, that should be function in a function. So we're looking for, is there a nice function inside another function? And yeah, we can spot one. Do you see this x squared plus 9? That's a function inside of the square root. So we have a nice function in a function. So that's sending a signal to us and saying, hey, look at me. I should be the substitution. And of course, we're paying attention. We're like, oh, you want to be the substitution? Looks good to us. We'll take you. We're happy to have you. So we say let u equal x squared plus 9. Now, why do we like this? Well, take the derivative of u. What do we get? 2x dx. And the key here is that we see an x dx. So we're like, nice. Now you might say, we were so close. That's a 3. That's a 2. But constants are so easy to work with. We can move constants around. So as an example, we say, look, 1/2 du is x dx. So this is how we can move constants around. We can divide both sides by 2. So updating our integral, we can say, all right, we still have the 3. The x dx becomes 1/2 du. All right, so there's 1/2 du. And then this x squared plus 9, well, that becomes u to the 1/2. Now remember, whenever you do a substitution, every single x has to become your new variable u, or, well, whatever your variables are being called. But every variable has to be replaced. So that's why it's a good check. If there was still an x here, we aren't done with our substitution. That or we chose a bad substitution to make. But this is looking promising. So we say, all right, great. We have our 3/2, which is our constant. And now we have our nice rule. This is one of our 10, something to a power. So how do you integrate? Well, you add 1 to the exponent, so that would be 3/2. And then you multiply by the reciprocal. So what's the reciprocal of 3/2? 2/3. It's almost like they wanted that to happen, right? Look at that. 3/2 times 2/3. Oh, wow. They planned this. This was rigged. This was rigged to turn out nicely. Are we done, by the way? Did we miss anything? Plus C. Yep, don't forget that. That's important. That's important. Okay, so finally, we say, here we go. Now you might say, haha, that's the answer, right? Probably not, because I wrote equals, so there must be something else. And the something else is, because we're doing an indefinite integral, we've got to go back to where we began. We started in terms of x. We have to end in terms of x. So that says, okay, everywhere there's a u becomes x squared plus 9. So x squared plus 9 to the power 3/2 plus c. And there we go. That's our general solution. Y equals that. I guess I should have written y equals. There we go. Good, good. Life is good. All right, great. Oh, this is nice to get back to doing integrals again, right? Got to get that practice in. And the more we practice, the better we get. All right, well, I think we should do one last one. And then we'll say, that's enough practice for this session. Okay, so here is a case where it's a second order because we have x double prime of t. Now, oftentimes when we think of second order, sort of our intuition is like, ooh, it's like an acceleration, right? It's a good way to think about things. Of course, it doesn't have to be, but that's a nice intuitive way. So we're told the second order, 5 times square root of t plus 3, and then we have some initial conditions. Namely, when we plug in 6, we get this number 88. When we plug in 6 into the derivative, when we plug 6 into the original function, we get 319. And the question is, okay, what is x of t? So what's different? In theory, there's really nothing different here. It's just that we are going to take 2 steps. We start with x double prime. One step gets us to x prime. Another step gets us to x. So now we're ready to begin. So x double prime of t. So first off, let's make this calculus friendly. And that means let's write this as not t plus 3 with the square root symbol, but as t plus 3 to the power 1/2. Okay, step 1. We're going to take one antiderivative. So x prime of t. Okay, well, take an antiderivative here. So 5, and then we're going to have t plus 3 to the power 3/2, and then multiplied by the reciprocal. Reciprocal of 3/2 will be 2/3, and plus a constant c. All right, now we could do another integral right away, but let's use our initial condition. So in other words, we say, hey, we know something about x prime. Namely, x prime of 6 is 88. So we want to plug that in and use that to help us solve for our constant as soon as we can. Generally speaking, it's good to solve for constants early when possible. As early as possible is the ideal. Well, we'll see lots of examples as we go on about things that we want to do. So we know that x prime of 6, well, that's 88. That's a big number. Okay, well, what is that? Well, that's 5 times 2/3 times 6 plus 3 to the power of 3/2 plus our constant c. All right, so let's dig into this. So 6 plus 3 is 9. All right, great. This is 9 to the 3/2 power. Now you could say, well, let's do 9 cubed, which is what, 729? And you're probably, maybe it is. Well, it's a big number, right? And then take the square root of that. Okay, another big number. But we don't have to do that. Here's something a little bit easier. Say, look, there's really 2 things going on. We're going to cube it, which makes something big, and then we're going to square root it, which makes something small. Well, let's do that in the reverse order. Let's take the square root. So let's make things smaller first before we make things bigger. Square root of 9 is 3. Yeah, we can handle that. Now 3 cubed. Just work your ways up. 3, 9, 27. Okay, so what we really have here is 5 times 2/3 times 27. And then plus a constant c. And we say, oh, great. 3 goes into 27. That would be 9. All right, great. So 9, and then times 5 times 2, that's like 9 times 10, which is 90. So that's 90 plus our constant c. And now we're like, oh, 88 equals 90 plus c. Hey, that's not so bad. c is 88 subtract 90, which would leave us with -2. Good, good. So now we can update. So really, say, hey, here's x prime of t. Well, we'll write as 10/3 t plus 3 to the 3/2 minus 2. All right. Hey, it feels great because we started with a problem involving x double prime, and now we're to a problem involving just x prime. We're halfway there. We have made great progress. Woohoo! Yeah! But we can get all the way. All right, so the next step, well, repeat. So let's integrate again. So we say, aha, x of t. All right, yes, we've already written down x of t. We're in the home stretch. Okay, so 10 thirds. Then we're going to have t plus 3. All right, add 1 to the exponent. That would be 5 halves. And then in the front, multiply by the reciprocal 2/5. Now, on a side note, you might be saying, are we cheating at all here? I mean, because you might be saying, hey, if it was like t to the half or t to 3 halves, I totally agree with what you're doing. But doesn't that plus 3 affect anything? If you're not comfortable with this, you can always do a u substitution, u equals t plus 3. But generally the thing is, if you are adding a constant, you don't need to really do anything. That plus the constant inside doesn't change the antiderivative, other than that there's that plus that constant that stays put. But if you're not comfortable, by all means, do what helps you feel comfortable. And yeah, just do a substitution. Okay, continuing forward. Don't forget we have to integrate the minus 2t plus another constant. Now, of course, you might say, oh, plus c. Since we've already used c, let's be careful because we don't want to confuse ourselves later on. So we should just work our way through the alphabet. Plus d. And there are some problems where we're going to really work through the alphabet. We're going to be like, wow, there's like 9 different things that we have to figure out. Ah, good times ahead. Good times ahead. Okay. All right, but back to our problem. We can, of course, do a little bit right at the front because we see 5 does go into 10. So that's good news for us. So that's like a 2 there. All right. Well, now what do we need? Well, we need to use our other initial condition. So, this x of 6 equals 319. We're going to plug that into the bottom. Okay. So what do we get? Well, we get x of 6 equals 319. All right, we're just copying that down. All right, that's 4 thirds times 6 plus 3 to the 5 halves minus, and then 2 times 6. Well, we can do that in our heads. 2 times 6 is 12. And then plus this unknown value for d. All right. Well, let's clean it up. 6 plus 3 is 9. Square root of 9 is 3. We've talked about that before. So we could write this as 4 thirds times 3 to the 5th. And then minus 12, and then plus our unknown constant d. All right. Now the nice thing is 3 goes into 3. So I can cancel off a 3. All right. That makes it a little bit easier for us to work through our powers. Okay, 3 to the 4th. Okay, well, 3 times 3 makes 9, times another 3 makes 27, times another 3 makes 81. So this is 4 times 81, subtract 12 plus our constant d. 4 times 81. Well, 4 times 80 would be 320, and then there's plus 4 more, right, because of that 1. So that would be 324, and then minus 12 plus d. And now we're like, whoa, this is great. So what is that? Well, 324 subtract 12, well, that's 312 plus our constant d. And we say, look, 312 plus what gets us to 319? Well, we can do that. In fact, that's what we can do in our head. So that tells us d should be 7. Ah, nice. Woohoo! Haha. So, yeah, these were really kind of big numbers, but they were big numbers that helped us get small choices for C and D that were reasonable to work with. All right, now are we done? We got our C, we got our D, and we're almost done. We have all our pieces, But remember, when we're looking for x of t, we should finish by saying x of t is this. So, putting it all together, we come to our conclusion that x of t is going to be equal to, here we go, 4/3, our constant in front, t plus 3 to the power 5/2 minus 2 times t, and then plus 7. And there we go. Life is good. All right, that was a lot of work today. And so we deserve a short break, but we'll be back soon because there's more to do, a lot more to learn. So I hope you have a great day. Take care.